In the last video, we verified the stress distribution on a circular rod subjected to torsion. In this video, we will compare the torsional stiffness of a solid and hollow rod of same mass. In engineering theory, we studied that a hollow circular shaft can have a higher torsional stiffness than a solid shaft when both the shafts have the same mass or same cross-sectional area. I will create two Abaqus models subjected to identical torque and boundary conditions, extract the angular displacement at the loaded end and calculate the torsional stiffness as K equal to tau by theta. If both the shafts have the same outer diameter, the solid shaft will be stiffer because it has a larger polar moment of inertia. To demonstrate the practical advantage of hollow shafts, I would compare the shafts of equal mass. In that case, the hollow shaft places more material farther from the center, resulting in a larger polar moment of inertia and higher torsional stiffness, which we will confirm by a smaller twist angle in the results. To compare the torsional stiffness fairly, I would create a solid shaft of 50 mm diameter and a hollow shaft with 60 mm outer diameter and 33.17 mm inner diameter, so that both have the same cross-sectional area and mass. After applying the same torque and boundary conditions, I would compare the twist angle at the loaded end. I will follow the same steps that we performed in the previous video to create both the static torque models and run the simulations. So now we have the results for two iterations, one with the solid rod and other with the hollow rod. Note that both have the same mass. I will use the meta post-processor for comparing the results. We will measure the angular displacement of both the results. In meta, first we will open the result files of solid shaft and hollow shaft in two different windows so that we can compare them. In both the windows, I have loaded the results for linear displacements. I will insert the annotations at the nodes with the maximum displacement in both the models. Note that these are linear displacements. For calculating the angular displacements, we will use the measure angle functionality. We will measure the angle with respect to y-axis before and after applying the load. Then we will take the difference, which will be the angular displacement. We will do this for both the models. For the solid shaft, we observe that the angular displacement is 0.1179 and for the hollow shaft it is 0.063. So the angular displacement for the hollow shaft is less than that of the solid shaft. So we can say that the hollow shaft has a higher torsional stiffness than the solid shaft of the same mass. Thank you for watching this video. Do let me know your thoughts in the comments.